Ben Serebrin. I work in the hypervisor group for Google Compute Engine at Google. And today I'm going to talk about how we measure the effects of turbo on our VMs, which is a fairly new thing we've been able to do. So to do this requires a decent background on CPU turbo, and this is sort of the documentation I wish I had when I started doing this. So it's scattered in a lot of places of documentation, and this is the primer I would write if I were rewriting the documentation. So CPU turbo is defined moderately the same for most CPU vendors. Most CPUs and computers can run different components at different frequencies, and they make different performance trade-offs, battery life or absolute performance or thermals. The general idea is that CPU turbo will run a few CPUs at different frequencies when the power and thermal margins allow. And so if we look at this picture here, it's a abstracted 2-socket machine, 12 cores per socket, and each core has 2 threads. And so the sockets are moderately independent in terms of their power controls. Each thread in the same core is tied together on frequency, and sometimes the cores are sharing frequency islands and sometimes they don't. It depends on the architecture, but in general I try to think about this as every CPU core might go at a different frequency. It depends on the architecture. When they go fast is when they can. Each part has a thermal limit and a power consumption limit. And so if they think they can go fast, they might do so. The transistors only go so fast, so there is an absolute maximum limit. So when CPUs are halted on the same socket or M waiting or in deeper sleep states, C states, the other cores have the opportunity to go fast. Conversely, they go slow when they're going to consume a lot of power. On Intel and AMD, there's this wide vector unit called AVX, and if that gets turned on, you usually use several hundred megahertz worth of performance frequency, and whether that's all the CPUs in the socket or some of them depends on the generation. And so as an example, I've got this graph here, which is taken out of the E5 processor line version 3. It has a whole bunch of cores in it, and when only one core is active and all the other cores are idle, we get to go really fast, 3.6 gigahertz on that blue line there. And as more and more cores turn on, we slow down all the cores because they have a maximum limit that they share until about half the cores in the socket are active, and then it stays flat on this particular generation. The graphs are different generation to generation. This yellow line, which actually rendered well, is AVX. So if some cores are in AVX, then they need to drop some frequency because the AVX units consume more power and produce more heat. This base frequency is something of a shared illusion I'll talk about in the next couple of slides. But these numbers make it hard to figure out which CPU is actually faster when they're using all the cores to do throughput-related things. You know, these are 3 different CPUs I sampled from various websites. They have a 2.3 or 2.2 sort of base kind of number. Some of them say 3.5 gigahertz, some of them say 2.7 gigahertz for their maximum, some of them don't say. Do you know which one is faster? You can't tell. So they all have this base frequency illusion, which is this red number that I never told you how CPUs run that fast or slow. The first CPU is probably talking about the turbo boost frequency when only one core is active over on the left side of the graph. The 2.7 is probably talking about the turbo frequency when all cores are active. The third one just didn't bother to say. So these make comparisons of both VMs and parts I buy for myself really annoying. And so to define this red line a little better, there's this number called base frequency, which is always equal to the TSC frequency, the timestamp counter, and that's important for timekeeping. So the TSC ticks as if it were a clock, it always runs. That's really useful, but it's not useful because it's also the advertised frequency, which the cores don't really go that fast. They usually go faster. The base frequency is some kind of somewhat hard floor of the frequency you'll drop to unless you go slower because you're in deep, dire thermal straits. So it's not particularly intuitive about how fast I'll go in the common case. The number that I like to use is when the cores are all busy, we're probably in the all-core turbo frequency, which is this purple line over there, purple box, where they all keep going at 2.8 on this particular part, no matter how many more cores light up. And that's more intuitive for how fast the computer can go when it's running all cores doing work. There's a similar plateau below that for the AVX running, and whether or not each core is affected by its neighbor being AVX is part specific, so I won't talk to that. But in general, this base frequency is the number that typically gets advertised, and it doesn't mean very much. So moving on to how I measure this. If I have a host machine, a native machine, I have a lot of capability to measure. This gets x86 specific and a little Intel specific. There's model-specific registers called APERF and MPERF that have been around for quite a while, both in AMD and Intel. They're not defined by themselves. The ratio is defined. and it indicates the ratio of total cycles you actually got, including the bonus cycles when you were going faster due to turbo, the ratio of that number of cycles to a constant clock, which is mostly TSC, but it might have a scale factor. So you can think of it as how much did I get turbo boosted. So if you have a 1.0, you didn't get turbo boosted at all. If you have a 2.0, you got a lot of turbo boost. If you were below 1, then you were in some bad thermal straits. APerf and MPerf both stop ticking when cores are halted, so if you're halted a lot, you're not going to go below 1.0. It's only going to tell you the turbo history you had when you were actually running. If you look at turbostat, which is in Linux tools, it has a bunch of formulas for calculating this. They use the APerf and MPerf ratio plus some model-specific information about C-states. They don't document the formulas, but they're fairly easy to read out of the code, and it's informative. On Intel, there's a few MSRs that tell you the current frequency, this 198 MSR, and then the 1AD through 1AF are actually the way you can read out the blue line on those graphs for any given model. And they read the manual because they change the definition of these registers at some point. Most of these MSRs, or all of these MSRs, don't get visible to VMs, so what do I do? VMs really don't know anything about what they're doing unless I tell them. They don't know what CPU socket they're on or how big it is. They don't know how many cores there are or how many sockets there are. They don't know where they might be running. Depending on your scheduler, VCPUs will move around the system, different sockets or same socket. They don't know the CPU curve, frequency curve they're on, or the frequency at the moment. And if I'm investigating a performance anomaly where things were fast, but now they're slow, or there's a lot of variation, this stuff has a large effect, but it's nothing the guest actually has access to in our systems. And that's really annoying and confusing. And so what do I care about this? So these anomalous performance events have a lot of different things that influence them. You might have unlucky scheduling. You might be next to a thread that uses AVX. You might be on a heavily loaded socket. You might be lucky and have an underutilized socket and then set your expectations badly. This is also useful to kind of know how much time I got stolen from a VM to do VM services. If the APerf MPerf absolute count was significantly less than the absolute count of TSC, I was paused for a long time. And that's a useful indicator of spending time servicing the VM or confusion about how it was halted or other things. And we have a lot of times where we get a good benchmark number when the system is idle, both internally and externally, and it looks really good because we had a lot of turbo upside, and then we run it on a machine that's shared, and things go slower. And I'm trying to incorporate our notions of the history of turbo for the VM into a way to understand whether we have got comparable results between A and B. So the code that I will aim to upstream in the next few weeks is relatively simple. We track per VCPU the histogram of residency at each 100 megahertz size frequency bucket, and we put them in debugfs for reading out. I'm assuming that processors aren't going to go massively faster or massively slower, so I set some constant overflow and underflow buckets at 1100 megahertz and 5 gigahertz, and then between those it's 100 megahertz buckets. I intentionally set them constant, and I didn't give any knobs to move the buckets around, because if you've got a histogram, you want it to compare to some other histogram on some other machine, and it doesn't take that much storage to just have this wide set of frequencies. So currently I wrote it in Intel vmx.c. It should be a pretty straightforward port for svm.c, and I added a disable module parameter to turn it off, but it will turn it on if it finds the hardware, and only really old hardware and nested hardware wouldn't support APerf and MPerf. The interesting choice we made was tracking vCPUs rather than the physical CPUs, because the vCPUs wander due to this scheduler. So I track the APerf and MPerf deltas accumulated while the vCPU is running CPU cycles. On the core it was on, and if it moved somewhere else, then I keep the track of the samples, the deltas on that new core. That gives me the effect of tracking the vCPU's turbo history in a consistent fashion as it moves around the whole system. And so to kind of describe the APerf and MPerf a little bit better, time goes to the right on this. Guest is the blue and host is the red pieces of time. So TSC, as seen by the guest, always increases because it's needed as a time source. MPerf increases when the guest is running and freezes when the host is in effect. And that directly is analogous to MPerf and APerf stopping when we're in a halt state or otherwise not running CPU cycles. MPerf always has the same slope as TSC, maybe with a scale factor depending on the hardware. And APerf slope is changes depending on whether we're in higher or lower frequency. And so APerf indicates the number of cycles we actually got. MPerf is the relative to wall clock cycles, and the ratio is the turbo goodness factor. So APerf and MPerf always are discontinuously paused during non-guest cycles. And this is a picture that's different for every vCPU because each vCPU in a VM might be having a different turbo and halting history. So we made a few trade-offs in the decision of aperf and mperf. Theoretically, we should probably count those cycles while we're doing something on behalf of the guest, intercepting and emulating CPU ID or MMIO. That gets really messy as soon as we hit any asynchronous paths where the hypervisor has to do work, might get interrupted, might go to disk. And in most cases, things are pretty quick, like CPU ID emulation, or really confusing, like asynchronous network or hard drive. So I'm just ignoring all the hypervisor time. We start the stopwatch when the guest is running in a VM run iactl, and we stop it when we're on the hypervisor. That's, I think, a pretty good trade-off. It loses a small amount of precision, but not very much. And then this is certainly enough to get intuitions about where the guest is spending its time and frequency losses. I use the same definition of average frequency. If you look in turbostat.c, that's what they call it. So we don't measure time in each frequency bin. You know, the CPU, in this case, has 100 megahertz increments. I can't see that. I can only see the aggregate cycles that were given. So if I spent half my time in 2 gigahertz and half my time in 2.1, it will be probably in the 2 gigahertz bucket, and that's pretty good. It's still a pretty good sampling. Given what we have from the hardware, we don't directly know why we were throttled. We can infer a few things, and there are hardware-specific ways to know more, but those are out of scope of what we're doing here. So as an example, just a 1 vCPU VM, the first tuple is the histogram, and the second is the histogram for all the VMs. So if there are more vCPUs, it's a histogram for all the vCPUs in the VM. So if there are more VMs, more vCPUs, we'd have more entries in the non-parenthesized areas. So this is just some histogram of the frequencies we had. And I also keep the TSC, mperf, and aperf overall history so we can actually calculate the overall lifetime frequency that the guest got, as well as infer how much time is stolen from the guest, which is available elsewhere, but this is convenient. So this is an example measurement, somewhat simulated, so I didn't have to get real numbers put in here. So if we look at the histogram buckets, we see a little bit of weight over out on the right where the highest frequency is, where we only can do that when there's 1 or 2 cores running. And then as we get to the all cores frequency at 2800 to 2899, there's a decent amount of weight at that one and the bucket below. And due to the way the histogram works, I would kind of think of those together, that we spent a good portion of our time in the all cores turbo frequency. But this workload had a significant amount of AVX going on, so we had that 2600 frequency, which is the AVX all cores turbo frequency for the part I looked at, which is interesting to know. There was AVX going on maybe in that workload, maybe in some antagonist nearby. And so we can dive in further with other tools to figure out, was this workload doing AVX, or is it being surprised by having a 300 megahertz loss? So this is the kind of investigations I've started doing. So as an example, if somebody says there's anomalous performance on this state, we can look at these things and say, what was co-located? Does it have AVX and this customer doesn't? Are there other things, maybe thermal events going on that we log, or high intensity workloads that can actually push you lower than the AVX frequency? It can also show us if we had more weight over on the right side where the higher turbo bins are, we can infer that the CPU got lucky and was scheduled on an empty socket or something like that, and know that this isn't necessarily representative of sharing the machine. And this is actually being pretty useful in an ongoing investigation we have about trying to find where these jitters and anomalies are coming from. So looking forward, I was considering exposing aperf and mperf to guests. The underlying counts make it possible to do so. With live migration and other concerns, it's confusing to give it to the guest directly. It seems more useful to have it as a host tool. If we move you to a different vCPU, a different physical CPU that has a different frequency or a different microarchitecture generation, aperf and mperf become inconsistent with the previous history, and now we need to define whether we zero them, notify the guest, try to manipulate them so they're consistent. It gets moderately messy. I also would like to see virtualized performance counters coming, and then the same kind of problems about inconsistencies with different frequencies or generations comes in there, and it gets rather interesting and messy. And so I would love to argue for a guest is profiling notification, both directions, where you can tell the guest, your world just had a discontinuity, but that's not for today's talk. So to sum up, and it's almost lunchtime, we have the ability to aggregate the turbo residency per vCPU, so we can see the history of each vCPU as it goes through the system, and try to get insight about why we're having good or bad performance relative to our expectations. And it's a way to try to set expectations when I know I've got an idle machine that's getting too much turbo. I should try to do something to my numbers to predict sharing performance. And I also am advocating for using the all-core turbo frequency as a comparison metric so we can understand the differences between CPUs in a better way than understanding base frequency. So, any questions?
So does the TSC differ between, so when you have a NUMA, 1 and 2, for example, doesn't the TSC differ somewhat between the two? So what if your VM gets moved from NUMA node 1 to, NUMA node 0 to NUMA node 1? How do you take that into account?
So does the TSC differ if you move between different NUMA nodes? So there is, I think starting with Nehalem, a CPU ID bit and host that says TSC is good for a time source. And so it's up to the system integrator to make sure that the TSCs on all the sockets are synchronized well, which is mostly around deasserting the correct reset at a good, well-defined time. And even if there's a little bit of jitter, it's not visible because the time to prove that you had a difference in TSC is hundreds of nanoseconds to talk between the cores. So I think that what I know of the design, they get it far below the detection threshold. And so if that bit is set by the hardware, then they've attested that they've done the right thing.
Yeah, possibly, and also because of averaging, I guess it just, possibly, and also because of aggregating it over time, it just drops, I guess. Okay, thanks.
Yeah.
So where do you get a perf and mperf? Is it at VCPU load and VCPU put, so in the preamp notifiers basically, or is it at VM exit and VM entry?
So I sample it at the beginning of the VM run IACTL and at the end, and at what did I do? Every several hundred microseconds in between to try to capture differences that would happen because the CPU can asynchronously change its frequency. So if I got a VM exit that will cause me to go back in without returning the IACTL, I'll sample it occasionally.
So you check how much time has passed so you don't do it too frequently?
Yeah.
Okay. And the other question is, because of the AVX penalty, could there be some workloads where actually using SSC for some things instead of AVX turns out to be faster because in the majority of the code that doesn't use vectorization, you actually can get boosted more?
So if I have a little bit of AVX, I should avoid using AVX to avoid the frequency penalty?
A little bit of SIMD, yeah. Can that happen?
Yeah, I think I'll direct you to Intel for details that I know, but don't know if they've been exposed. But if you look at some of the work they've done in glibc, I think they've been trying to optimize for that. And there's some AVX is more expensive than others, and they're trying to make the compilers a little more aware.
So despite the confusion of a turbo to the customers, do you think it's kind of worth still, enabling the turbo in VMs?
Enabling what?
Basically keep a turbo mode.
Right, well, they get turbo mode unless somebody disabled it, but they don't have a way to measure it directly.
Well, we can disable turbo, but you don't want to disable turbo.
The turbo is useful enough that I want to know when it happened, I want to use it, and I want to know when there's surprises from my expectation.
So as long as it's clear, when the turbo is kicked in, and that's good.
Yeah.
Okay.
After Paolo, there's a question way in the back.
So what's the overhead of measuring a perf and mperf every some time?
I didn't measure it directly because I amortized it. There's already a TSC read in the point where I need to know, and so when I do the TSC read, if not enough time has passed, I don't read the MSRs. So I assumed it was in the noise. The microphone is making its way back.
I wanted to add that the suggestion about using all-core turbo frequency is a bit deprecated because Skylake and AMD EPYC processors use different frequency curves, which make this flat all-core turbo basically inexistent. And the second thing is that, if I remember correctly, there are machine-specific registers which allow inspect whether we are hitting temperature or power limits. So you actually can observe why there is frequency limit for the package.
Okay, I'll try to restate that because there's no monitor actually aimed at me, so I heard part of it. I think you're saying there's differences in the MSRs for AMD versus Intel on controlling the power?
Not really. I am saying that on the modern processors, there are different frequency curves. That's the first thing.
Different frequency codes?
Yeah, dependency of maximum frequency based on the amount of cores active. It's far more lean on Skylake and Epic. Like you can have far significantly higher frequency on, for example, 20 cores than 28 cores on Xeon Platinum 8160, for example.
So you're saying that when I have lots of cores on the AMD parts or the newer Skylake parts, I have a different turbo curve?
Yeah.
Yeah. I mean, you can use the measurement here to infer the shape of the curve. This should be agnostic to what the hardware is capable of doing. It'll just measure it because APerf and MPerf are fairly standardized. So if I misunderstand your question, I'll come talk to you after. Cool. It's lunchtime. Anyone else? Thank you.